In 4.1, we learned about what discrete probability distributions look like. In 4.2, we're going to talk about special kind of probability distribution, and that's these things called binomial distributions. So a binomial experiment is a probability experiment that satisfies the following conditions. And there's going to be 4 of them. And to have something that is a binomial distribution or a binomial experiment, it needs to have all 4 of these parts together. So the first thing is the experiment is repeated for a fixed number of trials, where each trial is independent of the other trials, right? So you can do it for 10 times, you could do it for 20 times, you could do it for 1,000,000 times. There's just a set number of times in which you're running this experiment. And if something happens in one of the trials, that's not going to affect any other trial. So each trial is going to be independent and not affect the other ones. Secondly, there are only 2 possible outcomes of interest for each trial. And so just in this amount of generality, those outcomes are going to be classified as success, which is capital S, or failure, capital F. Depending on what the actual experiment is, let's say flipping a coin, the success could be getting a heads versus a failure, which would be a tails, in which case you would use H and F instead of S and F. The probability of a success is the same for each trial. So these things don't change from trial to trial. The probability of getting a success should be the same throughout. And then the fourth is that the random variable X is going to count the number of successful trials. So notation-wise, we have N, which is going to be the number of times a trial is repeated. P, which is the probability of a success in a single trial. Q is going to be the probability of a failure. And since there's only 2 outcomes, the complement of a success is a failure. So S prime is equal to F, which means Q is really the same thing as 1 minus P. And then X is going to be the random variable that represents a count of the number of successes in N trials. So we're first going to see if we have ourselves a binomial experiment. And then if we do have one, we're going to specify the values N, P, and Q, and then list out all the possible values of the random variable. And then if it's not a binomial experiment, we're going to explain why. So this first one, a certain surgical procedure has an 85% chance of success. A doctor performs the procedure on 8 patients, and the random variable represents the number of successful surgeries. We go through our checklist. First thing, there's a finite number of trials. It's fixed. There's only 8. Second, there's only 2 possible outcomes. Either it's a successful surgery or it's not. So that takes care of the second condition. The probability of a success is the same for each trial, right? So each time this doctor goes into the OR or the ER, 85% chance of success each and every time, right? So that takes care of that. And then the random variable is going to keep track of the number of successes. So we have that. Those 4 things all check out. And so, yes, this is a probability, or this is a binomial experiment. And the number of trials that we have are 8, with 8 patients. Probability of success is 0.85, right? Because 85% chance of success, which means our Q is going to be 1 minus 0.85, which gives us 0.15. And then we're asked to list out the random variable. So you can have 0 successful surgeries, 1, 2, 3, all the way up to all 8 being successful. Looking at this next example, a jar contains 5 red marbles, 9 blue marbles, and 6 green marbles. You randomly select 3 marbles from the jar without replacement. The random variable represents the number of red marbles. So you're going to pick out 3 marbles, see how many red you get, take them out, and then pick out another 3. Because this is without replacement, we're not replacing any of the red marbles that we get, which is going to change the probability between the different trials. So because each trial is not independent, this is not a binomial experiment. Trials are not independent. And that's coming from the fact that this is without replacement. If we were doing replacement, it might be a binomial experiment. But since we're doing it without replacement, each trial is dependent on what happened beforehand. And that leads us, once we have these binomial experiments, we can create these probability distributions. It's going to be discrete since we have a finite number of trials. And so in a binomial experiment, the probability of exactly X successes in N trials is going to be, well, you can have X successes. Then if you had N trials, that means that you had N minus X failures. And we want to take all possible combinations of successes and failures that has X many successes. So if you think about that, you could have success, then failure, or it doesn't matter if the successes are at the beginning, at the end, in the middle, what order they come in. And if you think about the end of chapter 3, that was a combination. So we want to have N choose X times the probability of success to the X power times the probability of failure to the N minus X power. And that gives us the probability of X number of successes out of N trials.